So, thank you, Rafael, and hello, everybody, and thank you for having me in your seminar. It sounds indeed very interesting initiative. And although I usually don't give talks online because I like to be close to people, I'm happy to be with you from far away. And well, I hope that my talk will not be too basic, or also I hope it's not going to be too complicated either, because I don't exactly know the composition of the audience. Um, so I decided that I'm not going to give a talk about a particular paper, but maybe give a little bit of overview of a number of things that I've been working on in the last few years. And somehow the one common denominator of these things, of these questions in geometry and physics, is the basic curvature tensor, and it's not necessarily the front runner of all these questions and problems, but it is something that ties up the structures together. So I used it as a prompt in the title, and my talk is based on various collaborations and also in many cases work in progress, because maybe I'm giving too many talks instead of sitting down to finish the papers, with a number of people, including Thomas Basile from Mons, Axel Hrelia, who's my PhD student in Zagreb, Chris Hall from Imperial, Noriaki Ikeda from Kyoto, Lara Jonge from Zagreb, Sylvain Lavaux from Galatasaray University, Dima Reutenberg from Amsterdam, and Peter Schupp from Bremen. And currently I'm actually visiting Peter Schupp in Bremen, so I'm saying hello from Bremen. Okay, so I will start with the first part. I understand that I have something like 45 minutes now and 45 minutes later. So I will start with an introduction. But before going into the blah blah, I will first start with a motivating, very simple exercise. That's truly very simple, but it will introduce us something, I believe. So suppose that I have a smooth manifold and I choose a linear connection on it, no metric structure, just affine. And of course, for any connection, we can write down its curvature tensor, which is the commutator of covariant derivatives minus the covariant derivative of the commutator of vector fields. And okay, for the sake of the argument, let's also assume that the connection is symmetric. So it is torsion-free. Torsion-free means that this second equation holds. And then we can do a little algebra, use the algebraic Bianchi identity for the curvature tensor, and then rewrite the curvature tensor in a rather unorthodox way. And this unorthodox way is written here. It's this big parenthesis that you see here. There is a minus in front, but I mean, it's maybe irrelevant. Okay, and then the point is that this parenthesis represents a primitive form of our main protagonist, the basic curvature tensor. So I will give it a separate name. I will call it S in the rest of the talk. And as you can see, what we have here inside the parentheses is something that tells us whether the connection that we have chosen is a derivation of the Lie bracket. So this is certainly what the first three terms represent. But of course, the first three terms by themselves are not a tensor. So to get a tensor, you actually have this antisymmetric combination here, where you have maybe this unorthodox thing that you have a covariant derivative along a covariant. In any case, so this is kind of the simplest way to see this kind of tensor popping up. Of course, in this context, it is nothing very surprising or very important, in the sense that we are in the setting essentially of the canonical tangent Lie algebroid, and in this case the basic curvature tensor is just the opposite of the curvature tensor, so they vanish together. But in general, the point is that this tensor has a separate life, especially for more general Lie algebroids, or even for higher structures than Lie algebroids. So we will see a little bit about this separate life of this tensor. But before that, I also would like to say one example from physics, because this is where I first heard about this tensor. So I got motivated to look further into where it appears. So in gauge theory, sometimes it might happen that you compute the algebra of gauge transformations. And this algebra is not closed off shell. So it closes only on the stationary surface. So when we take into account the equations of motion. And of course, many of you will remember that this is one of the main motivations for introducing the Batalin-Velikovsky formalism, which is the most general formalism to quantize a given gauge theory. Of course, there are other reasons. For example, you might have reducible systems like gauge for gauge symmetries, or you might have, which is not the case here in general, you might also have structure coefficients in your gauge algebra, which are field dependent. They are not structure constants. In all these cases, you need to do something to define your path integral. And this openness, as it's called, of the gauge algebra is one of these cases. Now, the setting where this basic curvature appeared was in the work of Ikeda and Strobel not long ago, in 2019, when they were trying to answer the question, what is the BV action of the twisted Poisson sigma model? Now, to come into this problem, let's think, first of all, that the simplest possible case, at least I think so, but I mean, you can argue about it, of having an open gauge algebra is the Poisson sigma model. Actually, open gauge algebras and all these motivations appeared in more complicated theories back in the 80s. But actually, the most simple case is the Poisson sigma model, which was found in the 90s. So the Poisson sigma model is a theory that has as a target space the Poisson manifold, M, with a Poisson structure by vector pi. And it is an interesting model from many points of view. First of all, it is a model that encompasses a lot, if not all, of several different two-dimensional gravity theories. The second reason is that it is the quantum field theoretical model that allows us to compute the star product, the conserved star product from a QFT, so the deformation quantization of Poisson manifolds. And it is also the simplest case in a class of models, which are very nice, which go under the name of AKSE sigma models, which essentially is a geometric way to encode the BV formalism. So the Poisson sigma model is the simplest in this class. And as mentioned, it's a two-dimensional gauge theory that has scalar fields and one forms. And when you compute the gauge algebra, you find that there is an extra term in the gauge algebra, which F is some kind of equation of motion here. It's the equation of motion for the one forms. And then it has a red coefficient, which is, well, of course, very simple in this case. It's the second derivative of the Poisson structure. But the point is that the geometric meaning of this coefficient is actually the basic curvature of some auxiliary connection. In the case of the Poisson sigma model, this is kind of unnecessary in the sense that you don't need any auxiliary connection really to write down the model, especially when you do the BV formalism. But what Ikeda and Strobel emphasized in 2019 is that this kind of geometric interpretation of the coefficients, it's actually rigid when you don't consider only the vanilla Poisson sigma model, but also what is called the three-form twisted Poisson sigma model, which is not based on a Poisson structure on the manifold, but on a twisted Poisson structure in the sense of Chevera and Weinstein. And what appears there, it's again the basic curvature tensor. And the interesting thing is that this model is not of an AKSE type. And this actually continues to being true for more general models. For example, on two-dimensional models that are based on Dirac manifolds, in which case you actually, to define the BV formalism, you can use two auxiliary connections instead of one. And this is some work we did with Thomas and collaborators a few years ago. So this is the physical motivation, let's say, the appearance of these kind of structures in the open gauge algebras, which, of course, as you understand, they also appear as coefficients in the quantum axiom. So it will appear as a coefficient in 4 fermion terms in the quantum axiom. Now, to the blah blah. So a little bit of brief history, at least, on these basic curvature tensors. Actually, I think that the first time that it implicitly appeared was in the study, in mathematics at least, was in the study of Cartan connections and Cartan-Lie algebroids about 20 years ago by Anthony Blau. But also implicitly, it appeared even. Was there a question? No. But also implicitly, it appeared a little bit earlier in a paper by Bolyó, Lossev, and Nekrasov when they were studying the target space covariant formulation of topological sigma models. They didn't define it there, but it's actually there. Then it was found again by Abad and Kreinig in 2009 when they were defining the adjoint and coadjoint representations of a Lie algebroid. And then, as mentioned, its importance was also emphasized when you try to construct the BV action of twisted Poisson sigma models by Atiyah and Strobl in 2019. Now, let me give you a little bit of context about what I'm going to try to talk about today. We will see how much I will manage to say in the time I have. I have plenty of time, but I will emphasize some things and maybe some things I will not have time, but we will see. So the first thing that I would like to discuss after an introduction is supersymmetric Poisson sigma model. Now, in general, supersymmetric Poisson sigma models were already defined, at least in the original paper of Ikeda on the topic, and then where he showed also how to write down two-dimensional dilaton supergravity like that. I think that a general study, a systematic study of supersymmetric Poisson sigma models was lacking, or is still lacking in some sense. In particular, I would like to emphasize that there was another model written down about 10 years ago by Arias, Boulazer, Sandel, and Torres Gomez, where they found a PSM, a supersymmetric PSM, that had some extra structure. Essentially, this extra structure corresponding to a global supersymmetry which was generated by the Dirac differential. So this is essentially based on DG Poisson manifolds. And I think this was a kind of single model, which was not studied much further. I mean, the motivation for writing down this model was to try to understand the deformation quantization, not only of the algebra of functions, but also of the algebra of differential forms, for example, or the algebra of multi-vector fields. And a systematic construction is something that we are trying to do. We already have some results, try to find some new models and try to classify them, and try to see what kind of types of global supersymmetry you can have, perhaps even more different than this Dirac supersymmetry that these people found in that case. Now, as you understand, a lot of this talk has to do about connections and tensors. So one other set of questions that I'm very interested in is about connections and tensors for Courant algebroids. So a set of questions one can ask here is the following. So first, one can try to ask, so if we know what is a basic curvature tensor, we will see about that for Lie algebroids, is there a corresponding notion for Courant algebroids? So I will try to answer this question today. The second, maybe even more interesting question is, what is the Riemann tensor of a generalized connection in a Courant algebra? Now, as you probably know, this is a topic that has many approaches. People have a lot of proposals about what a Riemann tensor can be, but somehow it feels like this is still an open problem, and most of the answers that have been attempted are kind of unsatisfactory in some sense. So I will try to revisit this question from a different perspective today. And the related question, of course, which would be of very interest for physics, is the question of whether you have a fundamental theorem of generalized Riemannian geometry. In other words, if there is a unique generalized metric compatible torsion-free generalized connection. The answer to this, as far as I know from the literature, is no. I will try to restructure the problem in a way that the answer is almost yes. So I will try to discuss this towards the second part. Then another topic which I'm not going to go into details today, but I think, okay, it's more technical, but it has some interest, is the question of whether this successful pattern that Ikeda and Strobl developed through these geometric notions, whether it still exists in higher dimensions. So if you try to consider, for example, sigma models in 3 dimensions, which are based on pre-Courant algebroids, like 4-form twisted Courant sigma models. And even in higher dimensions, if you try to do something which I call usually brain mechanics, which is like what Chevera calls higher dimensional Hamiltonian mechanics or higher dimensional AKSE sigma models. And indeed, this pattern in some sense persists, but of course you have to know what is the basic curvature tensor for some higher algebroid structure. The last topic, which I do have something to say in the end, but I don't know if I will manage to reach there. If not, I would like to even motivate you to invite Dima Reutenberg to tell you more about this. Is about the Atiyah class of DG manifolds, which is again a topic that has to do with connections, in the sense that the question here is how to study DG manifolds that admit a compatible linear connection, and then how to characterize the obstruction to this compatibility. And of course, this is related to some characteristic class, and this class here is the Atiyah class. In other words, we try to investigate DG manifolds with vanishing Atiyah class. I will see if I will manage to reach this point. So in the second part of my talk, I will now discuss how I will stay in the Lie algebroid setting or the super Lie algebroid setting at some point, and I will go towards this attempted classification of supersymmetric Poisson sigma models. So, okay, I'm afraid that maybe this is too simple, but for this audience, but then I don't know that. So just to set up my notation, maybe just let's take a quick look at Lie algebroids. So for Lie algebroids, the ingredients that we have are these three. It's a smooth vector bundle over a smooth manifold M. And then we have a binary operation on the modular sections of this smooth vector bundle. And we have also a smooth bundle map from the vector bundle to the tangent bundle over the base, which we call the anchor because it takes a section and it anchors it to a vector field. The properties that these structures have to satisfy so that this is a Lie algebroid is that the binary operation satisfies the Jacobi identity. So we have a Lie algebra structure on the modular sections. And also that it satisfies the Leibniz rule with the help of the anchor map here, or in an alternative way, another property, which is of course dependent on the rest, is that the anchor map is a homomorphism in the sense that it commutes with brackets. Now, disclaimer from in almost all my talk, brackets will be denoted without any additional decorations. So which bracket is which should be clear from context. I mean, here it's clear that it should be the bracket of sections, and this is the bracket of vector fields. And of course, we know many examples of Lie algebroids, which are interesting both in math and in physics. Lie algebras, tangent bundles, foliations, actions of Lie algebras on manifolds and infinitesimal symmetries, Poisson manifolds and Poisson Lie algebroids, the Atiyah or Gates Lie algebroid, and others. I'm not going to discuss them in detail because I suppose that most of the people are very familiar with this. And an alternative way to think about Lie algebroids is that they are a special case of the theory of homological vector fields on supermanifolds, as was shown by Weintraub some time ago, in which case the ingredients are much shorter. They are a graded manifold M. So this is now 1 in degree 1, and the vector field Q of degree +1 that has the single property that it commutes with itself under the graded commutator bracket. I like to call this a geometric zip file in the sense that all properties that we saw before are encoded just in this homological vector. And there is a special case which is of interest, of course, for us, which is Poisson manifolds, in which case one thinks about the degree shifted cotangent bundle of a Poisson manifold. And in this case, we also have a canonical symplectic structure, graded symplectic structure, which is compatible with the homological vector field in the sense that the flow is zero. I like to think of this business of homological vector fields in the motto of simplification, universality, and naturalness, in the sense that simplification, in the sense that you trade sometimes difficult notions with simpler notions like functions and vector fields. Universality in the sense that in a very simple setting, it encodes a lot of different structures. And naturalness in the sense that, as far as I've seen from the literature, and as far as I see also from my own work, many times in more traditional differential geometric terms, certain structures become very awkward to define, but they are very naturally defined in the graded manifold setting. Now, as mentioned, we are going to be interested in connections. So in a sense, we think here of unifying linear maps and connections. So I will consider a Lie algebroid, an arbitrary Lie algebroid, and a vector bundle V. And then an E on V connection will be a rule that allows us to differentiate sections of the vector bundle V along sections of the Lie algebroid E. And the definition of a connection is very simple. I will be calling it E on V connection, and much like brackets, I'm not going to use any decorative features. All connections will be just nablas. They should be clear from context which one is which. We will see later. So the first rule is, of course, that it's linear, homogeneous in the first argument, and then it satisfies this Leibniz. Now, when the manifold is a point and the vector bundle is a vector space, which is a Lie algebra, and V is another vector space, this gives us a linear map. When both E and V are the tangent bundle, this gives an ordinary affine connection, a smooth manifold. And when E is the tangent bundle and V is a Lie algebroid, this gives an ordinary connection on the Lie algebroid. And of course, defining the curvature tensor of such connections is business as usual. You just write down the usual formula. We are in the Lie algebroid setting. This is not something that would work so easily for Courant algebroids. And also let me mention that, of course, torsion is not always defined in the standard way here, but only when the two vectors bundles are the same. And it's interesting to think that when you are in the setting of a point with a Lie algebra, a flat connection is the same as a Lie algebra representation. And in general, flat E on V connections are called representations of the Lie algebroid E. Now, let's come to this point of basic connections and basic curvature. So we will consider the data of a Lie algebroid and an ordinary, in other words, TM on E connection. Now, whenever we have this connection and the Lie algebroid structure, we can induce canonically an E on E connection, which I will be denoting by a dot, as we see here, where we take the ordinary connection along the anchored section to define it. Now, for E on E connections in general, we can define a torsion tensor in the usual way with a canonical formula. And we can ask the question here, does a torsion-free E on E connection exist in this setting? And the answer is yes. And the way to do it is by averaging with the opposite. So what does this mean? This means that the connection that will have zero torsion is going to be this average, let's say, connection, which is the canonically induced one, plus a connection which is sometimes called the conjugate connection. I will call this here the basic E on E connection. So this is an E on E connection which is obtained from the ordinary one plus the Lie bracket of the section. Then you can ask, what is the curvature of these two connections? And this is what reveals the concept of the basic curvature tensor. So when you compute the curvature of the canonical connection, this is directly related to the curvature of the ordinary connection along anchored sections. When you compute the curvature of this bar connection, the basic connection, what you find is another tensor, which is exactly this basic curvature tensor, which is defined in this red formula here, as you see, the definition of the basic curvature tensor is, again, essentially the question of whether this connection we took is compatible with the Lie algebra structure. And again, to do this, to define a tensor, you need this antisymmetric combination of these terms, where now what appears here is a different connection, is an E on TM connection. So it's a little bit strange in a sense, right? It's how to differentiate a vector field along a section of the Lie algebroid, which I defined here. So this is also called the basic connection. It's the basic E on TM connection. You can complain, and you will have every right to do so, that I used the same notation for both, in the sense that they are nabla bar, because these are two different connections, of course. But of course, as you might know, there is a reason for this. And then you can compute also the curvature of this E on TM connection, and you find that it's the anchored basic curvature of the ordinary connection. So you see that the curvature of these two connections are both related to the basic curvature. Now, as I mentioned in the introduction, the first maybe place where this was really clarified very well, at least where I understood this concept, was when Abad and Kreinik asked what is the adjoint representation of a Lie algebroid. And what they found is that you need a new concept to define this, to define the adjoint representation, which is the concept of representations up to homotopy. So the ingredients for these kinds of representations, so we saw earlier ordinary representations, and the adjoint representation is not an ordinary representation. So the ingredient is now a graded vector bundle, this calligraphic V. There is a degree 1 operator from V to V that basically makes V into a chain complex. Then there is a E on V connection, nabla bar. E is a Lie algebroid, obviously. And then I denoted it nabla bar, as you understand it will be related to the previous one. And then there are two more pieces of data. The first is a degree 1 endomorphism valued twofold, omega 2, such that the curvature of this connection is not 0, as it would be for a representation, but it is controlled by this object here and by omega 2, and it is flat up to homotopy. The final set of ingredients is it's a tower of endomorphism valued n forms of total degree 1, which satisfies some recursion relations, which I didn't write here. But essentially what happens is that you have a structure operator where you sum up all the structures, and this is an operator here that squares to 0, which gives you exactly this recursion relations. So it's a differential. It's essentially a very close concept to the notion of Q-bundle. Okay, and then the adjoint representation of a Lie algebroid was found to be a representation up to homotopy, where the graded vector bundle is the adjoint complex. And the ingredients here are that the degree 1 map is the anchor map, or the map in this adjoint complex. The bar connection is the basic connection, so it has two legs, one from E to one part of the complex, and one from E to TM, which is given by exactly the formulas I wrote before. Then this two-form omega is actually the basic curvature tensor, because it satisfies exactly what is needed. So the curvature of this connection is equal to this, with a degree 1 map rho. And then this is actually a short representation because the basic curvature turns out to be closed under the differential induced by the basic connection. So all the other higher forms are 0. So this is just 3 terms. The coadjoint representation comes together with the adjoint, of course, and it's also a root where the graded vector bundle is the dual complex, and all the data are the dual data. Now, let me go to discuss a little bit how you used all this stuff to understand this classification of Poisson sigma models with supersymmetry. So first, we should think about Poisson Q supermanifolds. So recall that we are now in the Z2 graded setting. So we think of supermanifolds, which we can also think as parity shifted vector bundles for a smooth vector bundle E. And a Poisson supermanifold will have in coordinates degree 0 and degree 1 coordinates x, mu, and theta a, and it will have a Poisson bracket written here through this calligraphic P. And I mean, this calligraphic P is skew symmetric in these directions, also in these directions, and symmetric in when you take two degree 1 coordinates. And it is even in theta in these directions. This coefficient is odd in theta, and this is also even in theta. Now, of course, being a graded Poisson bracket means that it should satisfy the graded Jacobi identity, which is this red formula here. Now, what we want is also to have some additional Q structure. So this is something that is much richer than ordinary Poisson manifolds. In Poisson manifolds, you cannot really work in this setting here. So we think also of having Q supermanifolds, so meaning a supermanifold with an additional homological vector field. So one that squares to 0 will be denoted with small q here, Qs. And then you can think of combining these two structures together and define Poisson Q supermanifolds. So having this supermanifold M, the graded Poisson structure, and the homological vector field, such that the homological vector field is compatible with the graded Poisson structure in the sense written in this formula here. So this will define the target space of these models that we want to write. Alternatively, if you want to think in terms of DG-Lie algebroids, essentially, you can think of the degree shifted cotangent bundle over the supermanifold, and then you have two homological vector fields, Q and Qs, capital Q and capital Qs here. And you have also a graded symplectic structure. And the structure is such that everything works correctly. So the two homological vector fields are also commuting, and that they also, their flow is, and also there is a compatibility between them and the graded symplectic. I mean, these two structures are equivalent, of course. And now, having this kind of Poisson Q supermanifolds, we can use them in order to have a very general supersymmetric Poisson sigma model. So to define these models, we go in an analogous way to ordinary Poisson sigma models. So we have a target space. So here we have a Z times Z2 structure, right? The Z structure is the integers are in the first slot, the Z2 structure in the second slot. So the fields that we have here are a set of scalar fields x mu and a set of one forms a mu as before. We also have fermions now in the theory, and they are these theta a's and these chi a's. So these are scalar fermions, and these are one form fermions. And then you can write down an action functional as in the usual Poisson sigma model, which looks like this. Or if you want to expand it, you can expand it like this. So all the different coefficients of the graded Poisson structure will come into the game. Now, I'm not going to write long formulas about how the gates transformations are here and all that. But the point is that the gate symmetries are generated by the homological vector field Q in this way here. If you think of phi collectively as all the fields of the theory, note that the gate symmetries include also supersymmetries here. So these are the local supersymmetries of the model. In addition, the role of this QS is that it generates a global supersymmetry if it is there, if there exists a compatible QS, degree Z2 degree 1 homological vector field. And okay, of course, the equations of motion are basically given by this formula here. And the question that we have now is what kind of specific models does this model describe, and what is the role of the of this Z2 degree 1 homological vector field in these models. Okay, so to understand what kind of models you have, because of course this is much richer than just the Poisson sigma model, where it's, of course, it's also many models, but all models are of the same kind in a certain sense. So here models are of a different kind. So what we will do is first we will do an expansion to try to understand what kind of structures there are hidden in the super Poisson structure. So we expand in the fermionic coordinates like this. So I show here just the first few terms, but of course this expansion goes on. I mean, it's a finite expansion, it's not infinite. It goes up to the rank of the vector bundle. And then what you find is that, so the expansion of the first coefficient, the first term, the leading order, is a Poisson structure on the base. So this means that the base manifold also has a Poisson structure. Then the leading order term in the mixed coefficient transforms like a connection. So the super Poisson structure includes in itself a contravariant connection. Contravariant means that it's a T star n on E star connection. And the leading order term in the degree 1 super Poisson bracket is a symmetric tensor, G, possibly degenerate. I don't. There is no reason here to be degenerate or non-degenerate, to be non-degenerate. But what happens? What one concludes from the graded Poisson structure, from the graded Jacobi identity, is that this symmetric tensor is covariantly constant with respect to the contravariant connection, whose coefficients are these gammas here. Now, of course, there are many more tensors here, or sorry, many more objects here that appear in the expansion, whose geometrical meaning is maybe less clear. And in fact, to understand a little bit better what is going on, at least for me, as a physicist, when I write down an action functional, I would like to have it written in terms of tensors and not in terms of other objects that don't transform tensorially. So to actually have this expansion, of course, is not an expansion in tensors. So to make this expansion an expansion in tensors, one can pay a small price. You can choose a splitting. You can split your supermanifold by choosing a TM on E connection. And then you can define tensorial components, which I will denote by this P nabla. So these tensorial components are, well, of course, the first one is just tensorial anyway, the P mu nu. But the mixed one and the other one, the AB, are not tensorial. So they become tensorial like this, but this is the definition here. And then you can, when you write down the compatibility conditions between the graded Poisson structure and the homological vector field QS, you get a very nice form of these compatibility conditions, assuming at least, okay, so here I made the assumption that QS is a homological vector field that corresponds to a Lie algebroid. In general, this is not so. Of course, we have a more general form of these equations, but QS is a Z2 homological vector field, so it doesn't have to be associated to a Lie algebroid, but let's assume that it is here. Then you get these very simple compatibility conditions between QS and P. And you see that what appears here is the basic connection, is the basic curvature tensor. Well, T is actually the anchor of this Lie algebroid associated to QS. And okay, a D nabla is the Lie algebroid differential defined by the basic connection. So the goal here is essentially to solve these conditions together with the graded Jacobi identity, right? To find examples that have this condition. But now the point of this slide is that when you write the action of the supersymmetric Poisson sigma model here, you get a covariant version of it. So you get a covariant exterior derivative here, and then everything in the action is written as a tensor. So that's the advantage of this rewriting. Okay, so now let's look at some examples. Okay, so the first example is Jacquier-Teitelbaum supergravity. So this supergravity theory in 2 dimensions. So what we do in this case is, in this expansion that I showed you, we keep only the leading order terms. So this is kind of a mixed case because the symmetric term, the G term here, is in a sense of order -2 Poisson bracket, degree -2 Poisson bracket, whereas the other two are degree 0 Poisson bracket. So when you take only the leading order, in this case, we take the target space to be the dual of the orthosymplectic algebra 1,2, so that we get the Jacquier-Teitelbaum supergravity. The Grady-Poisson structure is linear, of course, because the dual of a Lie superalgebra. QS is 0, so there is no global supersymmetry in this case. There is just the local supersymmetry that we have in supergravity, right? The connection here is essentially gamma matrices, so it's a representation, right? The symmetric part is also given in terms of these gamma matrices. And then they are 2-dimensional gamma matrices, of course, and then there is the 2-dimensional chirality operator also. And then you can write down the axiom functional, and it is exactly the axiom functional of Jacquier-Teitelbaum supergravity, with the dilaton and the spin connection and all the gravitino fields all in place. So this model is included in this way, but in a rather trivial way, and it's the QS equals 0 case, which is the case that was found like 30 years ago by Ikeda and others. Now there is a second case, which is this differential Poisson sigma model. I will take 5 minutes to discuss this, and then I will make the break. Right? So this case is when you take E to be the tangent bundle, and then you choose the Poisson structure to be all the terms at degree 0. So we are asking now here about a degree 0 Poisson structure compatible with a homological vector field, right? So this is the mathematical problem. So we take the Poisson structure to be given like this here. So R is an unknown thing at the moment, okay? So for the time being, it's just an unknown thing. It's the quadratic term in the thetas here. And I wrote this in the non-covariant way, but when you covariantize things there are no gammas, things look like tensors here. And then the homological vector field in this case is the Dirac differential. Okay? Now, when you ask for the compatibility of the homological vector field with the Grady-Poisson structure, you get fixed this coefficient R. And this coefficient R turns out to be the curvature of the opposite connection to the splitting connection that we took. Of course, now we are in the tangent battle, so the opposite connection is just, the connection with the opposite index structure. With an index raised with the Poisson by vector pi. So in fact, here I wrote that another condition is that the Poisson structure on the base is covariantly constant with respect to the basic connection. This is in fact a choice. It's not something that comes out from the compatibility conditions. Sorry about that. So that's a choice here, which was made also by these people in constructing this model originally. And then this is a compatibility condition, which is solved when you have this. But essentially what we have here, as you can see, is the basic curvature secretly, because it's the curvature of the basic connection. You can write down now the classical axiom functional, but now that you have satisfied the conditions, it looks like this. So it has a kinetic sector for the bosonic fields and for the fermionic fields. It has this Poisson sigma model type of term, and it also has this quartic fermion term. So this is the classical axiom, okay? So no quantization. And then the quartic fermion term is controlled by this coefficient. Now, if you write down how much is the QS, so the lift of the ramp differential, of course, in the full tangent target space. So in this way, you can see that this QS is exactly the coadjoint representation up to homotopy for the tangent Lie algebroid. Which makes sense because, of course, these are the coefficients of the basic connections, and this is the coefficient of the basic curvature tensor in this case. Now, let me do the case 2b, and then we take a break. So the case 2b is the contravariant version of this model, which is new. So now if you take the cotangent bundle instead, so that your target space is this, so you have a field content again, and there is a choice again of coefficients. Again, this R here is unspecified for the moment. You write down the model looks similar to the previous one, but we have to find what this R is. So how do we find it? By asking again the mathematical problem of having a compatible homological vector field with a graded Poisson structure of degree 0. And then what this does is that it fixes this quartic term here to be minus the basic curvature. So these R, don't get confused with curvature. This is not a curvature, okay? It's just the coefficient, the quadratic coefficient in this expansion. So it turns out to be the basic curvature tensor, which in this present case has this complicated form in coordinates, but maybe this doesn't matter. So this is another model where what appears here is directly the basic curvature tensor, nothing else. And then the supersymmetry of this model is generated by the Lichnerowicz-Poisson differential. I actually forgot to write this. So here in this case, you have the Lichnerowicz-Poisson differential, and then the supersymmetry is generated by this. So the supersymmetry in this case, first of all, is non-linear supersymmetry, unlike the previous case. And it's generated by the Poisson structure in a way, again, that you have the coadjoint representation of homotopy, that it corresponds to this supersymmetry transformation. So I think this is the first time that I see something like this, that a Poisson structure, first of all, controls supersymmetry transformations, and also it's a non-linear supersymmetry by itself, because the Poisson structure in general is not linear. And then what ties these models together is that the supersymmetry is generated by the coadjoint representation of some Lie algebroid. Now, this doesn't work in general, okay? So these models are kind of singled out. If you take an arbitrary Lie algebroid, you will not really be able to solve this condition so easily. Okay, is this a good place to take a break?
Perfect one. Let's say, yeah. Let's.
Okay, so we take 15 minutes break, which means that we reconvene. 15, yes? Is it okay?
Okay, it's fine for me, yeah.
Yeah, so we reconvene at 3:20 Warsaw time.
Okay.
I would like to ask you this question, because you said this additional connections and additional structures on the Lie algebroid. So do you have a clear interpretation of these structures in terms of this graded manifold, similarly as this Lie algebroid structure corresponds to the homological vector field?
Yeah, so if I understood correctly your question, because it was not visible here, well, of course, there is a super Lie algebroid structure. This was already this has been studied mostly by Mehta. So yeah, there is a super Lie algebroid structure here in the which is associated to the homological vector field.
Okay, but do you have the further part of this dictionary between Lie algebroids interpreting these connections and other higher structures in terms of graded manifolds?
Further dictionary, in which sense do you mean that?
So that the Lie algebroid structure corresponds to the graded manifold. So what is now exactly this connection from on the Lie algebroid, or this action of the Lie algebroid in terms of graded manifolds?
That's a great question. Okay, that's a great question. So what connections correspond to in the graded manifold setting is going to come towards the end of my talk a bit. And this is something that we are still studying it, but I will show you towards the end of my talk about this, okay?
Okay, thank you.
So that's a good question to ask me later. Okay, so now, can I continue?
Sure.
Okay, so in the second part of my talk, I will try to have 0 indices, okay? So the indices were not very popular. Just let me finish a little bit with a couple of remarks about what I was talking before. So first of all, there is a very rich structure of supersymmetric Poisson sigma models which haven't been classified completely, and we haven't also classified them completely. There are still things to be done here. The second thing is that one has to look at the quantization of these models to see what kind of, in the same way that Cattaneo and Felder, for example, did the quantization of the Poisson sigma model, what happens when you quantize these supersymmetric Poisson sigma models with this global supersymmetry. And the third thing, which is, I think, interesting here, is whether this kind of structures exist in higher dimensions, whether there are analogous statements for supersymmetric Courant sigma model. And I think also that the general mathematical problem of studying given Lie algebroid structures compatible with even Poisson brackets is something that I haven't seen being studied, to be honest. And as far as I checked with Dima Reutenberg, this is something which is not known. I think this is like a problem which is underlying this discussion that I had before. Okay, now to go to a territory with 0 indices, I will now discuss some things about Courant algebroids and connections. So just a quick reminder to set the notation. So for Courant algebroids, we have again a smooth vector bundle. We have again a binary operation, which I will call the Dorfman bracket. We have the anchor map, and we have also a non-degenerate symmetric bilinear form, which I will denote in this talk by eta, okay? And by eta sharp, the corresponding map. And then this satisfies 3 properties. This data satisfies 3 properties. The first property is that the binary operation satisfies this left Leibniz algebra identity. So it's not a Jacobi identity; it's a Leibniz identity. So the model of sections has the structure of a Leibniz algebra and not of a Lie algebra. And then there are 2 compatibility conditions which basically control the symmetric part of the bracket of the Dorfman bracket and the compatibility with the inner metric. Okay, so this is my notation for this part of the talk. And then as before, I'm interested to start thinking about connections and tensors. So first of all, I will consider an ordinary connection on the Courant algebroid. The definitions are the same as before. And we can ask the question whether this connection is a derivation of the Dorfman bracket. So this is the same question we were asking in the case of Lie algebroid. And then the answer to this should be some kind of basic curvature tensor. So indeed, there is a way to define a basic curvature tensor here of this ordinary connection on the Courant algebroid with respect to the Dorfman bracket. The first point that one can note is that the basic E on TM connection can be defined as before. So same definition. And it is still a good connection, good linear connection. And then you can define the basic curvature tensor. Now the E's are sections of the Courant algebroid. X is a vector field. And then you have, in black terms, the same kind of structure that you had for the Lie algebroid case. But then it turns out that this is not a tensor. So what makes this a tensor is this additional term here, which involves again the basic E on TM connection. And this object is what you can call the basic curvature tensor with respect to the Dorfman bracket. Okay? Now, some comments about this. First of all, you see that there is a non-canonical definition in the sense that it's not the same as before. It has a little bit bizarre looking additional term, right? So this term tensorizes the structure, as we said, the object. And it's very similar to what Marco Gualtieri did in defining a torsion tensor for generalized connections. So generalized connections are E-on-E connections in this setting. And Gualtieri defined this torsion tensor here. And as before, you see the naive definition for the torsion tensor is not a good definition because this is now the Dorfman bracket. And since it's not skew symmetric, it doesn't satisfy the Leibniz rule in both entries. So there is this correction term that Gualtieri introduced to define the torsion tensor. Mm-hmm. I will come back to this in a moment about what I would say is a torsion tensor in this context of Courant algebroids. Then notice also that if you ask where is the other basic connection, which was the E-on-E basic connection, okay? If you write the naive formula as before with the Dorfman bracket, which is this one here, this is what Jodslin calls a Dorfman connection. So in fact, it's not a connection. You can easily see that if you put a function in the lower entry here, this doesn't come out. So, well, I write it here actually, yeah. So the connections, these connections, if you want to call them connections, are not homogeneous. However, you can think of writing down this formula for a basic E-on-E connection, which involves an extra term. Now, this sounds a little bit ad hoc here, but I will try to argue in a moment that it's not ad hoc, that it has a meaning. Maybe the point here is that there is a fork in the road, exactly because the Dorfman bracket is not skew symmetric, so it doesn't satisfy Leibniz rule in both entries. There are more than one directions that one can go here to define meaningful tensorial objects. Moreover, there is no canonical definition of the curvature tensor for E-on-E connections here. There is an interesting proposal by Branio Jurzo and Jan Wysocki about what could be a curvature tensor, but it's not a definition I'm going to use here. And there have been in the literature a lot of other approaches where they define a Ricci tensor directly without defining a Riemann tensor. I'm not so fond of this approach, but I mentioned. So now let's go back and think of Courant algebroids as Hamiltonian vector fields, because I want essentially to go in the direction of defining canonical tensors. So we know from the work of Reutenberg that the Courant algebroid can be described as a symplectic submanifold of this second order bundle, the cotangent bundle of a vector bundle E. So this is what is called sometimes in the maybe in the physics literature a QP manifold. So here we have the homological vector field Q, and we have also a canonical degree 2 symplectic structure, which is compatible with the homological vector field. And as such, one can define a degree 3 Hamiltonian function using the Poisson bracket, the graded Poisson bracket induced by the canonical symplectic structure of the cotangent bundle. And the Hamiltonian function satisfies, of course, this classical master equation, if you wish. And one can find these structures described through the Courant algebroid as derived structures in a sense. So the Dorfman bracket is a derived bracket. You can compute it as a second Poisson bracket with a Hamiltonian. The anchor map is computed again by Poisson brackets, and the inner metric of the Courant algebroid is just here the Poisson bracket. Now, this is not the way that I want to go. There is an alternative way to think, which is exactly taking the other road in the fork. Okay. So in general, when you think of QN manifolds, before introducing without having any graded symplectic structure, it's known that split Qn manifolds are Lie n-algebroids. Now, a Courant algebroid is in general not a split QP2 manifold. Okay. So to actually split it, you have to pay the price, and the price is again to introduce an ordinary connection of the Courant algebroid, which is compatible with the inner metric, with the non-degenerate bilinear form. Now, once you do this, you split the second order bundle into a graded vector bundle, which is this one, which admits a Lie algebroid structure. Now, this we can do only with the connection, okay? So this is not a canonical construction. It's a construction that involves a splitting. But now, the nice thing about this is that you can derive, you can have higher derived brackets, which are infinity linear for k higher or equal to 3. So the derived brackets are given like this, where the object that you have here is the part of the homological vector field with homological degree k minus 1. So the homological degree you obtain from the unweighted Euler vector field. So you take the graded commutator bracket of the Euler vector field with Q, and then whatever has eigenvalues k, so this is the homological degree, is this Qk. Okay. Now, of course, for Q1 manifolds, which are Lie algebroids, there is only one k equals 1. So the whole homological vector field is in the same homological degree, which gives the Lie bracket of a Lie1 algebroid, which is a Lie algebroid. So there is no fork in the row. So whatever you do is the same. But for when you go to degree 2, the situation is not the same. So for Courant algebroids, there are 3 different homological degrees. So there are QKs for k equals 0, 1, and 2. So as expected here, so since there is 0, 1, and 2, there are 3 kinds of brackets. There is 1 bracket, 2 bracket, and 3 bracket. Okay? So we computed these brackets. So the Lie algebroid structure, or this graded vector bundle, is given by the anchor map, rho, and by the following 4 brackets. So the only non-vanishing brackets are these 4, because you have now something in degree -1 and degree 0, and all these brackets are of degree 2 minus k. So the L1 bracket is degree 1. So what it does, it takes a differential form, lambda, and it gives a section of E. So this is given like this with the dual of the anchor map. There is an L2 bracket, which takes 2 degree 0 objects and gives degree 0 object. So section to section. It's given like this. So so this bracket obviously has the properties that we like. So it is graded skew symmetric. So in this case, skew symmetric. And it satisfies the Leibniz rule in both entries. So this is a different bracket, both from the Dorfman bracket or from its possible adisymmetrization, which sometimes is called Courant bracket in the literature. So this is a different bracket. Then you can write also a Lie2 bracket, an L2 bracket, which takes a degree 0 object, a section, and a degree -1 object, one form, and it gives one form. So it's degree 1. And there is an L3 bracket, which takes 3 degree 0 objects and gives 1 extra, and gives an one form, which is degree -1, because the degree 3 bracket is 2 minus 3 minus 1 degree. And the degree 3 bracket involves some basic curvature tensor. So the basic curvature tensor here is not the one of the connection which we used for splitting with respect to the Dorfman bracket. It's the one with respect to this L2 bracket, which is greatly skew symmetric and satisfies the Leibniz rule. The formula for this basic curvature tensor, it comes out to be canonical. So it's this definition which has no additional red terms, right? So it's a canonical definition. So it looks like when we use this Lie-2 algebroid structure, paying the price of introducing a connection that splits the second order bundle, you get canonical definitions. Okay. Now, in this case, when you write down the basic E-on-E connection, it is exactly this. So it is as it was for Lie algebroids, but instead of using the Lie bracket of the Lie algebroid, you use this L2 bracket of the Lie-2 algebroid that comes from splitting. Okay. Now, again, I emphasize that this bracket is skew and satisfies Leibniz rule, so in both entries. So this is a great bracket. Now, let me mention that Sylvain Lavaux has proven that another choice of connection gives an L-infinity quasi-isomorphic Lie-2 algebroid. So in a sense, all these connections are, the splitting, it doesn't really matter. Now, having this connection, this bracket, which has these nice properties, we can define tensors by construction. So you can define with the canonical formulas without any need to start checking whether something is a tensor and then correcting it so as to be. Just write down the canonical formulas that you would expect, just putting everywhere the L2 bracket. So both this object and this object, so now this is a generalized connection, okay, are obviously tensors. And also we have the basic curvature tensor, and all definitions are nice. So they are canonical. They are as you would like them to be. Now, I would like to mention that when you take this bullet connection, so when you take this canonically induced connection as your E connection, and only for that, this torsion tensor that we defined here is identical to the definition given by Gualtieri. But it's not identical for any other E-on-E connection. Okay. Also this canonical induced connection is very special because you can also write down the naive curvature tensor and then it's always a tensor. So the question was never about this connection, but about the general connection. Now the extra that you get, the bonus that you get from this approach to defining these tensors is that you get on the nose Bianchi identities. So you get both the first and the second Bianchi identity, so the algebraic and the differential Bianchi identity, which follow just by construction, by the L-infinity relations. So you write down the L-infinity relations here, the L2 relations, and they give you the Bianchi identities. So as far as I know, for all types of curvature tensors that were defined before in this generalized geometric setting, I have never seen Bianchi identity. So here the Bianchi identities you get on the nose. Okay. So I think I like very much this kind of definitions of curvature tensor. Sorry, there are some local coordinates also, but I just wrote it for completeness here. Okay, now this is the answer to the question of what we would like to think as the curvature tensor. And now we would like to introduce a generalized metric, okay? In a sense, having a generalized Riemann tensor. So we introduce now a generalized metric. So we take an endomorphism of E, orthogonal endomorphism, and we define a generalized metric like this. And now we can explore the question of what happens when you ask your generalized connection to be generalized metric compatible. Okay? So that the generalized metric is covariantly constant with respect to the generalized connection. Now, in the setting of this Lie-2 algebroid, you can write down a generalized Koszul formula. So this was never the case for any other definition of generalized connections and Riemann tensors. So the generalized conjoint formula looks like this. Okay, of course, you can see that the first part is what you would get in ordinary Riemannian geometry, basically. The point here is that on the right hand side, there is no dependence of the generalized connection. So with the definitions given before for the torsion and curvature tensors, the formula bites its own tail. So you have the generalized connection from the left-hand side, but you have it also on the right-hand side. So here it doesn't happen. So the right-hand side doesn't have generalized connection. So in this case, you can have a generalized conjoint formula. So essentially, the generalized connection is fully determined by the contortion tensor, which is defined like this, by the distortion tensor, which you might want it to be 0, of course, if you have metric compatibility. Well, actually, I mixed things a little bit in my slide. I'm sorry. This is the distortion tensor, which is not when you have non-metricity, but okay, just set this to 0, actually, because you would like the connection to be metric. And then you can determine fully the coefficient. So this is as close as we can get to a fundamental theorem of generalized Riemannian geometry. Okay, the catch here is that we paid the price from the beginning that we had to split. So we had to introduce a TM on E connection to split the Digi-manifold. Now, one application of this is to try to understand whether you can, because from the very beginning, the whole question about defining a Riemann tensor for generalized geometry was whether you can write the low energy effective action for closed strings or other structures, other kind of theories like double field theory as a generalized gravity theory. Right? So indeed here you can define a Ricci tensor by tracing, and you can define a Ricci scalar. Actually, you can define in principle two Ricci scalars. One is a Ricci scalar that you can write with respect to the generalized metric. One is a Ricci scalar that you can define with respect to the inner metric. Okay? And then for the data that you have from a Lie n-algebroid with the price that you paid, and the generalized metric, and the generalized connection in the volume form, you can write down an action functional like this. The same action functional essentially was written by Gyurczo, Muchka, and Vysocky, but in a Palatini formalism, but using different curvature and torsion tensors, which were not in this canonical form that we saw here. Now, Rafael will be happy that I will hide things under the carpet, and I will not go into the dirty business of introducing indices. But if you make suitable choices here, you can reproduce the low energy effective action for closed strings. And of course, a nice advantage I think that this formalism has is that you can now start asking questions of computing higher derivative correction. For example, you can ask even mathematically the question of what is the Gauss-Bonnet combination in generalized geometry. So what is the Gauss-Bonnet tensor? Okay. Now I have about 15 minutes. So I will skip the discussion about touristic Courant sigma models. It's maybe a little bit too technical. And I will go a little bit in a different topic, which has to do, I think, with the question that the gentleman earlier asked. I'm sorry, I didn't catch who it was. And I will give you some comments about the Atiyah class. So this came about as a question in trying to understand how all these connections and tensors come from in the graded geometry setting. So I think this was exactly the question. So now let's go directly on the graded geometry setting. Let's consider a graded manifold and take an ordinary connection on it. So M is a graded manifold. Okay? So we take an ordinary connection. I will denote this by a grave here to distinguish it from connections on ordinary differential geometry, right? Now, we will also assume that this connection is of degree 0. So when you take the Lie derivative with the Euler vector field, you get 0. So that it satisfies these conditions. So, of course, I mean, this is just an ordinary connection, but with signs, right? So functions pull out from here, and the Leibniz rule has signs. But of course, remember that the symbol nambla carries no degree, right? And of course, you can define in a canonical way torsion and curvature tensors. There's no question about what is torsion and curvature here. So the only difference is that you have signs and that you have the graded commutator bracket appearing everywhere. Of course, you can also define E on V connections in this setting, E on V being DG vector bundles. I will not need this for what I'm discussing here. Now, suppose that we also have a homological vector field, and then the question is the homological vector field compatible with this connection that we defined, that we chose? So what the answer to this question is the Atiyah cocycle. So the Atiyah class, actually, but one starts by defining the Atiyah cocycle for any specific connection. This, I refer here to the work of Mechtasti, Nono, and Su. So this is a degree 1 cocycle. So we take a DG vector bundle V and the DG Lie algebroid E. And the Atiyah cocycle is defined with respect to a degree +1 operator Q in this way here. So the cohomology class here is independent of the choice of connection. So you have an Atiyah class. I want to actually, at the interest of time, I want to specialize this to the case of a DG manifold. So let's take both V and T to be tangent DG vector bundles, and E in particular to be the tangent DG Lie algebroid. Okay. So then the Atiyah cocycle for a DG manifold is defined by this simple formula here. So it's the graded commutator bracket of the homological vector field with the connection. Okay. So the properties of this Atiyah cocycle, well, first of all, the obvious property is that it's a cocycle. Right? So it commutes with the homological vector field, as you see. The Jacobiator of the Atiyah cocycle is equal to this. So it's not 0, of course. So it's a co-boundary operator. The graded symmetric part of the Atiyah cocycle is equal to 0 for when the connection is has vanishing torsion. But when the connection has torsion, it's not 0. It's this here. And also, when you take two different connections and you compute the Atiyah cocycle for them, the difference is a co-boundary. So essentially, it doesn't depend on the connection. The Atiyah class doesn't depend on the connection. Okay. So now what we wanted to do is to characterize this Atiyah class, okay, for DG manifolds and understand when the Atiyah class vanishes. So to do this, we have so far understood this problem only for degree 1, okay? So for N1 manifolds, non-negatively graded manifolds of degree 1, and the associated Q manifold. So forget for the moment about the homological vector field, okay? So take a graded manifold, so a graded vector, take a vector bundle E over the base. So I will denote the base here M0, and I will denote by M1 the degree shifted vector bundle. And ask the question, what is a degree 0 connection? So TM1 and TM1. Now to understand this, first of all, I mean, recall that when you take the function ring of M1, there is a canonical isomorphism between functions and the algebra of differential forms, of E differential forms, and that the function ring is freely generated by this by degree 1, right? By sections of E star, essentially, which is a C infinity model. Now we want to look at vector fields on M1. The vector fields are concentrated in degrees -1 to the rank of the vector bundle. And there is canonically a surjective map like this. Okay, so every vector field, you can write it as a degree 0 or degree -1 vector field, and tensored with some function from the function. Now this map is surjective, but it's not bijective. So we would like to improve on this and try to understand whether there is one can construct a bijection here. But first note that for vertical vector fields, so the ones that annihilate basic functions, so vertical vector fields of degree k are the same as sections here. And in particular, you can see this in the simplest case of k equals -1. So for k -1, vector fields of degree -1 are sections of E, which is obtained through the contraction map, right? So you have the contraction map, give a section, and you get a vertical vector. Now, for vertical vector fields, there is a bijection from the vector fields of degree -1. Okay? So there is this canonical bijection, which doesn't need any other data. But this is not for all vector fields. And of course, to address all vector fields, you have to look at the horizontal ones also. So to fully describe the vector fields on M1 in these terms, first we think that the degree 0 vector fields on M1 are, was there a question? No. Are sections of the Atiyah algebroid of E star. So in order to separate the vertical and the horizontal vector fields, we have to split the Atiyah sequence. So we take the Atiyah sequence, we consider a splitting. So this is the symbol map, and then the splitting is this S check. And the splitting is the same as having an ordinary connection on E star. So once more, we pay this price of introducing an ordinary connection in E star, defined like this. And then this gives a bijection, which is of course non-canonical. And it tells you that all vector fields can be described basically like this, using this splitting. In other words, you can have generators of the vector fields being the contraction operator and this connection that was introduced through the splitting of the Atiyah sequence. So having these two objects, we can completely characterize now connections on the graded manifold. What we found at first stage is that there is an equivalence between such connections, and for data, so the first datum is an ordinary connection on E, on the vector bundle E, on the Lie algebroid. The second is an affine connection on the base manifold. I will denote by nabla circle. And then there are two tensors, T and K, which are not fixed here. Okay, so they are just arbitrary tensors living here. And you can find directly that you have these four formulas that tell you how the degree 0 connection on the graded manifold is characterized in terms of the vertical and horizontal. Now, to make this a little bit more specific, let's ask what is a torsion-free connection, okay? So a torsion-free connection on the graded manifold fixes the values of this T, of the torsion of the ordinary connection, and the adisymmetric part of this tensor K that appears here. And what you get is that a torsionless degree 0 connection on the graded manifold is associated to three data. So again, a TM on E connection, a torsionless TM0 on TM0 connection, and a symmetric tensor, U, this symmetric tensor now, which you can see that the adisymmetric part of K is fixed to be the curvature of the TM on E connection nabla. So this is what characterizes degree 0 connections on graded manifolds. So far we had no homological vector field. Let's now think a little bit about the homological vector field. So you remember that, yes.
Excuse me, as an organizer, I'm obliged to remind you that we have 5 minutes to the end of our allocated time.
Okay, I need 5 minutes. So the bracket of the Lie algebroid is obtained as also as a derived bracket. So then you can see that the canonical induced connection nabla dot is obtained by this formula here. So by computing this graded commutator of the homological vector field with the vertical iota, the conjugated connection, so the basic connection, is obtained by this formula here. And of course, one can define, as usual, in the space of connections, you can define in one parameter family. You take this convex combination, and this is a one parameter family of connections. For example, when you take k equals 1/2, you get the average connection, what I call the average connection. So these are how these connections are encoded in the graded world. And then one can go and compute the Atiyah cocycle. Okay? So we completely characterized the Atiyah cocycle. So okay, now this looks a little bit complicated for the last few minutes, but these are the precise formulas for how the Atiyah cocycle looks like in terms of all this data that characterized our connection. And let me give you just one quick, so that I leave a little bit of time for questions. What does the vanishing of the Atiyah cocycle give? So if you take a torsion-free connection, degree 0 torsion-free connection on the graded manifold, the conditions for vanishing of the Atiyah cocycle is first that the torsion of the induced connection vanishes. The second is that there is this bullet connection, which is a TM connection on TM plus E. And then the anchor map is covariantly constant with respect to it. There are these two conditions that are obtained for U, for the symmetric tensor U. And then there is this additional differential condition that you obtain for the tensor K, for the full tensor K, which I remind you is the sum of the symmetric tensor U and the curvature tensor. I don't have time, and I'm not going to discuss examples, but there are many examples that one can construct by understanding this vanishing of the Atiyah class. One option would be, for example, to invite Dima to tell you about this example. I think this would be interesting. Let me go to a brief outlook, and then I'm done. So the basic curvature tensor, I think it appears naturally both in the study of connections and representations of Lie algebroids, but also it appears in the study of connections on Courant algebroids and beyond. I didn't discuss it, but in fact, one can define some notion of basic curvature tensor for higher Lie n-algebroids. It also appears quite naturally in physical settings where you have this kind of structures, for example, in sigma models. And it also gives, for my taste, very nice canonical definitions of tensorial objects that we can use in generalized geometry. And in particular, these objects are important in order to understand how to construct gravity models in this set. As I mentioned, we are also interested in this mathematical problem of standard connections on DG manifolds and the Atiyah class. And I think that one very interesting open question here is, what is the Atiyah class of a Courant algebroid? So we haven't worked it out yet. So what I showed you, what happens for Lie algebroids. But I think that although often you might hear that there is no such thing as a Atiyah class of Courant algebroids, I think there is an Atiyah class of Courant algebroids, and this is something that I hope that in a future occasion we will have the chance to discuss. Okay, I will stop here, and I will be very happy to hear from you questions.
So thank you very much.
Thank you very much for your presentation, and yeah.
Thank you.
And there is a short question session. Is there anybody
Okay.
who would like to ask a question?
Andrew has a question, I see.
No, I'm
No,
okay.
it
I was
seems-
just clapping.
Sorry.
Okay.
Sorry. I'm sorry. I apologize.
Okay, so it seems that we are a little bit overwhelmed, so we have to think about what you have shown us. Thank you very much again for your presentation. The next meeting of our seminar will be in 2 weeks. There will be, of course, an announcement and later a reminder. Thank you once again.
Thank you. Whoever wants to ask a question separately can send me an email. I hope that you have my email. So just write to me.
Sure.
Okay.